Welcome. Today's notes worksheet is entitled Rational Functions Day 1. We'll have the opportunity here today to develop some of the basic characteristics of rational functions, and then we'll spend some time diving a little deeper into the complex algebra and doing some applications as well. So let's start it out here at the top. First and foremost, a rational function, this family that we're going to be looking at over the next couple days. It is a function comprised of a quotient, so a fraction essentially, of two polynomial expressions. And as you can see, I gave you a nice looking example right up here. Just f of x equals x squared minus 1 divided by x plus 2. So there's our quotient, so to speak, and polynomial in the numerator and a polynomial in the denominator. And really, we can't have a constant in the denominator, so that variable has to be down there as well. And that looks pretty good. We're going to do a variety of investigations to kind of take a look at some of the graphical characteristics that come up from these equations. And so let's start with really the most basic rational function. If you guys would just box that up for me, that would be great. Just y equals 1 over x. And so we'll go ahead and take a look at this on the graphing calculator here. I think I might have one available. And so if you have your graphing calculator, that would be great. And if you can go ahead and just go to your y equals. In fact, I have mine typed in, ready to roll. And if you could type in just that 1 divided by x, and then hit graph for me, and you should see that nice looking graph right there. Sort of two parts of the curve. Well, right there and then right there. Not the ideal window, but I think it should suffice here. So if I can impose on you, can you get just your coordinate plane going just in your paper there that I left a little room for you, and then let's go for it. Here we go. So here's one part of our curve. We've got that discontinuity here, which we'll talk about. And then so the second part of the curve, kind of over there, something like that should do. And then potentially you've seen this before, but the graphs of these rational functions go by a particular name here, and these are called hyperbolas. So we'll take a look at all different types. And obviously the more complex the rational function gets, the more complex the graphs are going to get. And so we'll obviously investigate that over the course of the next few days. All right, I'd love to dive a little deeper into some of these graphical characteristics and see where they come from and how they relate to the equation. So I'm going to kind of go board from board here, and you guys obviously just keep taking a look at that front side of your paper. So looks like I have some notation that we're going to take a look at right here. And just as a matter of fact, as I'm thinking about it, let's kind of split those up. That's how I'm going to divvy them up, right like that. And I guess this first part, for lack of a better word here, I'm going to investigate what we would call the discontinuity of the graph. Okay, so discontinuity right there. And just as I'm thinking about it, in a few minutes we'll get to this, of course. But that second piece, we will be exploring what is called the end behavior of the graph. So if you get an opportunity, throw that into the mix. And then potentially that'll relate, obviously, to our characteristics, the domain and the range. Okay, so let's see what we want to do with this piece. I think we need to interpret this notation first. Then we can go ahead and analyze the graph accordingly. And so what this says, as x approaches 0, and then you have this little negative symbol right there. That negative symbol has a little meaning, and so let's write that in. Basically what it means from the left side of 0. So that little negative symbol just means we're coming at 0 from one particular side. And what I want to know is what's going on with the y values there. What's going on with f of x? So f of x is approaching something. So let's go back to that graph there. Let me go to my previous board. You guys have it accessible already though. So here is your horizontal number line, of course. So these are all our x values. And what I'm going to do, obviously, is approach 0 from the left. So here is an x value of 0. I'm going to approach it from the left. And what I want to know is what's happening graphically, what's happening to those function values as I do come closer and closer to 0 from the left. All right, so everyone, if you would, hop on that graph somewhere to the left of 0. And let's get closer and closer and closer to 0. And what's going on with the graph? Well, first and foremost, I hope everybody does realize that the graph is decreasing. It's going down and down and down. And as x gets closer and closer to 0 here, and we are on the graph of the function, I'm hoping you see that this will just keep going down and down and down forever and ever and ever. And so as a result, those function values are going further and further into the negatives with no end in sight. So the way I would interpret this is that the numbers are getting greater and greater, but into the negatives, and so it's really, as I get closer and closer to 0, those function values are getting closer and closer to negative infinity. Now again, we have this discontinuity at the number 0. So now I want to focus on this piece, what's going on as we approach 0 from the right. So again, if you get an opportunity there, let's see if I can get an arrow going for you. So that plus symbol means from the right. Same deal. I'll go back aboard here and let's go ahead and see what's happening. So obviously, here's 0 on the horizontal number line. I'm to the right of 0, and I'm coming at 0 from the right. Okay, and as I get infinitely close to 0, what I want to know is what's going on with those y values. What's going on vertically? What's going on with those function values? And so let's go on that graph. Here we go. I'm tracing it. Very nicely done. Getting closer and closer to 0. I'm still to the right of 0. And as I get closer and closer to 0, I see that this graph is just increasing and increasing and increasing. And isn't it just going to keep going up and up and up forever and ever and ever? As we get infinitely close to 0, I would make the argument those y values are getting larger and larger and larger in the positives, so they would be approaching infinity. Okay, and you notice, of course, what happens at 0. Well, I mean, you look at the equation here, and can I actually have an x value of 0? No, of course not. I can't do 1 divided by 0, and so 0 would be excluded from those x values, and hence excluded from the domain. So as we come right over here, again, we kind of looked at the fact that we have a discontinuity at 0, and so as a result, our x values can be anything except for 0. So this discontinuity obviously affected the domain. All right, and in one direction, the functions are going down. In the other direction, they're going up. Okay, very good. Now let's go get the next piece. Actually, I'm sorry, one thing first. Let's go ahead and highlight this discontinuity. So again, what we said is basically that that x value of 0 is eliminated from the domain. And so what actually happens here, again, maybe you've seen this before, but essentially we get a boundary line to the curve of the graph of this function. And you can see here it's getting closer and closer to this vertical line. Here it's getting closer and closer to this vertical line. Is it ever actually going to touch that vertical line or cross it as I come from both directions here, both the left and the right? No, absolutely not. So this vertical boundary line to the graph actually has a particular name. It is what is called a vertical asymptote. See if you can spell that right for me. There we go. Not too bad. So there's our vertical asymptote right here, a vertical boundary to the graph of the function. And as you can see, it's right when x is 0. There is the vertical boundary line, right at 0, where the function is undefined, where we eliminated our value from the domain. Those are obviously intertwined. Very cool. Let's go get the next piece. Now we're ready. So in this case, we're looking at what's called the end behavior. As x is getting larger and larger and larger, as x approaches infinity, what's going on specifically with those y values? What do they seem to be approaching? So let's go ahead and see this in action, of course. When I say x is approaching infinity, what I'm basically saying is x is getting larger and larger and larger, so I'm just going to keep shooting to the right on my horizontal number line there. And let's hop on that graph and go to the right. So what's going on graphically here as we go to the right? Well, it seems like it's decreasing. It's going down. Is it plummeting like we did over here? Is it just going to shoot down and down forever and ever? No. Analyze that graph. It looks like it's plateauing towards a particular number. It's still going down and down and down, but it looks like it's leveling off toward a particular number. And I hope you would be in agreement vertically. It seems like it's getting closer and closer and closer to 0. Is it ever actually going to hit this this boundary line right here? No. I almost gave it away. What's it called? All right, so regardless, I'm hoping you would see that the y values here are getting closer and closer and closer to 0. Wonderful. Okay, let's go ahead and do it from the other direction. So as x goes to negative infinity, so horizontally what that means, we're going further and further to the left. This would be x going to negative infinity. And let's go ahead and analyze the graph. As we do that, hoping everybody sees that it's increasing, but it's not increasing in the same way as what we saw here. It's more of like it's plateauing towards a particular number. And as you can see, everybody, it seems like it's getting closer and closer to the x-intercept, like before. And that means that the y values are getting closer and closer to 0. In this case, as we go to infinity and to negative infinity, are we ever going to get y values of 0? No. But those y values are getting infinitely close to 0. And so as a result, just in this particular case, it looks like the range vertically is we have a discontinuity again vertically at 0. Let's go back and see it in action. Here we see it right here coming to the left. Here we see it going off to the right. And you get what is called, and this is what I almost said before accidentally, a horizontal boundary line, which of course is called the horizontal asymptote. So two boundary lines that we're looking at here today, the vertical asymptote and the horizontal asymptote. And in this case, we have a horizontal asymptote right at the y value of 0, meaning the function values, in this case, in the end behavior, are going to get closer and closer to it, but never quite touch or cross it. Now, one quick note, and then I'll move on to the next piece. A vertical asymptote, there's no way around it, guys. The graph will never, ever, ever touch or cross the vertical asymptote right here, because the function is undefined, end of story. A horizontal asymptote, just FYI, is a little different. Theoretically, a graph can cross the horizontal asymptote somewhere in the middle, but then eventually come back up and get closer and closer and closer to it. So a horizontal asymptote is slightly different than a vertical. Okay? So we'll see that in action as we progress and do some more complicated functions. Beautiful. So let's do this quick question right here and then hit investigation 2. It says, what is the sole restriction when determining the domain of a rational function? And, a rational function, obviously we're talking about a fraction. And what do we have to be careful of in a fraction? The denominator can't be 0. So that's what I'll highlight right up here. Unlike some of the other families of functions, in this case, a very specific restriction. The denominator can't be 0. So as a result, anything that would make the denominator 0 must be excluded from the domain. No other thing is out there that's going to affect it except whatever makes the denominator 0. So when I go into this investigation number 2 and I have you look at these 3 functions, function f, function g, and function h, well, if I ask you for the domain, you don't care about the numerator. We'll take a look at the numerator potentially on the next notes worksheet. The denominator is what I care about. So it says the investigation 2, talk about the domain of the rational functions and the graphical effect at the excluded values. So we've probably already set the foundation for this, but let's highlight it a little bit here. All right, let's go for it. Function f. If I asked you for the domain, again, look at that down below. Is there a number that would make that 0? Yeah, -5. And so as a result, x simply cannot be -5. I cannot perform that calculation mathematically with this particular domain value, and so it's excluded. Cool. Let's go to function g. And same deal, of course. I've got to exclude a couple of these. In this case, I'm going to exclude 2. 2 squared minus 4 would give me 0. That would be bad. But also -2. Just don't forget about that piece. -2 squared minus 4 also would give me 0. And so as a result, those are going to be excluded from the domain. Now here's what's interesting. This one over here, again, when we talk domain, obviously, we're talking about the real number system. And, I'm thinking this in my mind at least. I know that denominator can't be 0. And so I bring that 9 on over, just still thinking mathematically about it. And then I undo a square. And, then I start to realize, really, is there any real number here? No. It looks like when I solve this, I'm talking about imaginary numbers, and so as a result, there are no real numbers that need to be excluded. I hope everybody sees that in this particular case. So in this situation, the domain is all real numbers. There are no real numbers that would make the denominator 0, and hence there are no exclusions. We'd love to just keep getting used to the graphing calculator with these, so we're going to graph these functions right here. And what I want you to focus on is just what happens at those values. What do you see popping up? So you will not see function values at -5 for that first one. What happens there? All right, so again, get comfortable with this. You're going to be graphing a ton of these, so obviously you want to get a little practice on that with me and watching the screen here. So first of all, parentheses around the top, then a little divided by there, and then parentheses around the bottom. You have to just be careful here, otherwise the graphing calculator potentially will interpret it incorrectly. All right, I'm going to just do zoom standard again. It's probably not the best window for it, and I see that it's not, but that's all right. It serves our purpose. Here's part of the graph of the function right here, part of the hyperbola, and then another part is somewhere probably over here, give or take, and it's just tough to see with this particular window. But again, irrelevant. On the 83s, they actually do pop up. If you have an 84, you probably don't see it, but it is still there. Do you see this vertical line right here? Is this part of the graph of the function? No, absolutely not. Is it a vertical boundary to the curve of the function? Yes, and that's what's happening here. If we were to really hone in on this, we would see this is going to get closer and closer to that vertical line. It's not going to touch it, and it's not going to cross. Okay, so we get a vertical asymptote there. Wanted you to see that one. I'll go ahead and do this one relatively fast. If you can stay with me on that, that would be great. So I'm getting x squared, and how about -4 there? Again, same deal. I don't know if this window is all that great, but it should suffice. And you can see it's a more complicated graph of a rational function there. A couple things to note on this. Look at x equals -2. Do you see the vertical asymptote? Look at x equals 2. There's the vertical asymptote. And by the way, just because I'm seeing it here, I might as well go ahead and emphasize it. Do you guys also see a horizontal asymptote as the graph goes to infinity to the right and -infinity to the left? Do you see that horizontal asymptote right there? Cool. And do you see actually in the middle, though, the graph actually crosses that horizontal asymptote? Again, it can do that with the horizontal. We'll never, ever do that with the vertical. You can see on the vertical, it's come closer and closer from both directions, but it's not going to touch or cross. On the horizontal, it does. That's what's kind of interesting. But in the end, it won't touch or cross it. And we'll continue that conversation. All righty. Let's do that last one there. So we had vertical asymptotes at our 2 exclusions, of course. I'll be relatively fast on this one. So I've got 2 divided by, how does x squared plus 9 sound? I'm going to actually change my window in a hurry here because I seem to remember this one. By the way, do you think we're going to get any vertical asymptotes here? Remember, the domain was all real numbers. Do you think we'll get any vertical asymptotes? And take a look. Kind of a bell-shaped curve on this one. Any vertical asymptotes? No, absolutely not. No discontinuities, so there's no boundary line at this point. All right, hope that works for you at this stage. So conclusion, a 0 of the denominator, so whatever we exclude from the domain, produces a vertical asymptote. There's where we're getting them. All right, super. So the graph is going to approach it, but will not touch or cross it. Hey, it would be really great here if you could do example 1 by yourself. Just kind of pause the video for a moment and get right into it. So just real quick, find the vertical asymptotes, or singular or plural, for each function. Well, let's see how you did here. So function f, if I'm looking for the vertical asymptotes, it's where I would have the exclusions in the domain. And so in this particular case, I'd look to the denominator, and I see that denominator as factoring to x minus 5 and x plus 2. And so as a result, One value that would make the denominator 0 would be positive 5, and the other value that would make the denominator 0 would be negative 2. So we would write this in terms of the vertical asymptote. Remember, a vertical line is described as x equals a particular number. That's how we model a vertical line on the coordinate plane. And so x equals 5 would be a vertical line on the coordinate plane. That would be a boundary to the graph. X equals negative 2 would also be a vertical line on the coordinate plane. That would be a boundary to the graph. If I asked you for the domain of this function, sorry for bringing this back, then it would obviously look something like this right here. Obviously, numerically, they're intertwined, but essentially they're just talking about two different things. One is the domain, one is the vertical asymptote, even though, again, they really come from the same thing. All right, how about function g? Any values going to make the denominator 0 here? Nope. And this is the second time seeing it, so keep it in mind if you get an opportunity. But if there are no exclusions from the domain, then really should not be a vertical asymptote here. All right. Doing great. Would love to do investigation 3 relatively fast. Just interesting graphical things that occur with all sorts of functions. So this will be just a very quick investigation on the multiplicities of the vertical asymptotes. See if we can come up with a quick description on it. I'll be relatively fast, and if it doesn't click for you, just let me know. This is definitely a minor characteristic, but just one that's sort of intriguing nonetheless. All right, well, let's go do it. So I'm going to type in 1 divided by, and in parentheses there, just x minus 1. And I hope you would all agree, of course, that there should be a vertical asymptote at x equals 1. Shouldn't be any doubt in that. So let's go ahead and see that. I'm going to zoom in number 6. And there it is. Again, it's not ideal. But there's our x equals 1 vertical asymptote. The graph is approaching it going to negative infinity from the left. And guys, it's going upward, so it's approaching infinity from the right. Does everyone see that? So one it's going down, the other it's going up. Keep that in mind. Okay, what happens when I change the multiplicity? And we've talked about multiplicities before, and we will continue that discussion. How about multiplicities on the asymptote? What happens when I go squared on that? Take a look at the graph. Here's the x equals 1. There it is, right there in all its glory. And do you see now the graph is kind of going the same direction as we approach it from the left and right. The f of x values are both going to infinity. Does everyone see that? All right, let's go change this. What if I change it back to an odd multiplicity? Do you think they're going to go same direction or opposite directions from the left and from the right? Ooh, now take a look. There's your vertical asymptote. Now this one's going to negative infinity. This one's plummeting. This one's rising. It switched again. This one's going down. This one's going up on both sides, from the left and from the right. Kind of cool. Hey, one more time. Again, trying to be quick for you on it. But do you see it? What do you think when I change it back to an even multiplicity? What's going to happen? Well, tough to kind of tell here, but first and foremost, there's our vertical asymptote right there. And do you see, in this case, from the left, it's rising. From the right, the graph is also rising. And I could just keep doing that back and forth, odd versus even. And it's kind of interesting. We might graph a few equations, and that might be a little trick that we might utilize. Excuse me. So anyway, here's what I have. If a graph has a vertical asymptote of odd multiplicity, then the graph approaches the asymptote really, here's how I wrote it, just from different directions. One's going down to negative infinity, the other's going up to positive infinity. Cool. If a graph has a vertical asymptote of even multiplicity, then the graph approaches the asymptote from, and I just wrote, the same direction. Either they're both shooting up to infinity from the left and right, or they're both shooting down to negative infinity from the left and from the right. And just you happen to see them both shooting up to infinity here with that. If I did just a quick change, and just again, thinking out loud, you don't have to worry too much about this. If I flip that over, put a little negative, now do you see again? They're approaching the vertical asymptote, which is right here. This is going to negative infinity. That's going to negative infinity. Kind of cool. Just interesting little connections between equations of functions and graphs of functions. Obviously, it's a cause and effect, essentially. Cool. One more investigation. We can kind of put this together. So we've got a bunch. I'll shortchange it to just some degree. Maybe I'll do a little and you do a little, and we'll fill in some information. But this is the key, is now the horizontal asymptotes, which of course deal with end behavior. So just where it says end behavior of rational functions, this is going to relate to the horizontal asymptotes. So throw that into the mix. And I'll show you what I'm looking for here. We might just go ahead and analyze this graphically. Again, I'll give you a couple just to expedite this along. And then I'd love for you to kind of pause at some point and see if you can find the pattern yourself. So here's what we're looking at. And by the way, they'll take just a little bit to develop, but once we do, oh my goodness, it's a nice, easy pattern, and we should be able to talk about end behavior very fast. So here's what I'll ask. Let's all do this one together. Type in 2 divided by x minus 1. I'm going to hit zoom in number 6. And remember, what I'm looking for here is the end behavior. End behavior means what's going on as the graph is going to infinity on the right, and the graph is, really as x goes to negative infinity on the left. And so what happens here is we shoot off to the right on the graph. What's going on with those y values, and what's going on with those y values as we go to the left. So you could probably interpret this graphically. I can get a good sense of this just looking at it right here, what the y values seem to be approaching. But I'm also going to go ahead and utilize one of the other functions on the graph just to see it. So I'm going to utilize the table. Does everyone kind of see that right above the graph button right there? So everyone hit second and graph, and you can get a sense of it. And you could change the set on this. There's this function right up here. We can kind of change it, but I'm fine as it is. And basically all I'm going to do is see what happens is x is getting larger and larger and larger. Can I start to get a sense of what's going on with those y values? Now again, theoretically, guys, we're talking about x going to infinity. I'm in the 40s and 50s here. Obviously, I'm not doing that justice. But even still, I can still kind of tell what's going on with those y values. It seems pretty apparent that these y values seem to be getting closer and closer and closer to 0. If I did this and did this again and again and again, will I ever actually get a y value of 0 here? No. As x gets larger and larger and larger, these y values are going to get closer and closer to 0. And as a result, we have this boundary horizontally. Well, I should say a boundary line that is horizontal in nature at 0. So here's what you're going to write in, long story short. The y values getting closer and closer to 0. And so as a result, everybody, we have a horizontal asymptote at y equals 0. Okay. I'm going to do one more relatively fast here. And then I'll go ahead and give you the other one. If you want to pause the video at any point in time and just kind of do one yourself, I would strongly recommend that. But it's up to you. So I'm just going to hit graph, and really can't tell much from the graph. That's pretty useless. Oh, and by the way, the right end behavior and the left end behavior in these situations will produce the same idea. So theoretically, I could go to the left if I wanted to. I think it's just easier just to go to the right, so I'm doing that. All right, well, let me get to my table. I'm at 121. And in this case, take a look at my values. And again, I just want to make a good deduction here. As x is getting larger and larger and larger, what do you notice about those y values? They're decreasing, but they seem to be approaching something. And what are they approaching? 0. So again, guys, if you would, the y values are approaching 0, which means at the end of this graph, I should have a horizontal boundary line at y equals 0. All right, now everyone, should be noted, the last one is the exact same. So those in the top row, and obviously I did this with some purpose, all have a horizontal asymptote at y equals 0. You're going to have to think about why that is. The next row, guys, not the case. And let's see why. So new function. Let's reboot here, and let's do this one together. So bring up the calculator. I'm going to go ahead and graph that. Please do it as well. And you get 2x plus 3. And how about divided by, and let's go with an x minus 4. All right, really nice. I'm going to hit graph. And you can tell it's a little different here. Definitely have that vertical asymptote right here. Now if you look, just going horizontally, this one, it goes through 0, and it's still increasing. So definitely not a horizontal asymptote of y equals 0. It looks like we're above 0 when we get that plateau. And here I know it's a little tougher to tell, but same deal. I don't think this looks like it's plateauing well before we're going to get down here. I could be wrong on that piece, but I don't think so. So let's just hit the table, and let's see. All right, so, I'm just below 200 at this case, and, it pales in comparison when we're talking about x approaching infinity, but regardless, I can still tell. And look at those y values. They're getting closer and closer and closer to a particular number, and, logic would tell us it's getting closer and closer to 2. And that is what happens here. So y's getting closer and closer to 2. As a result, we have a horizontal asymptote. Oops, sorry. I got into it from before. So used to putting in the 0, but it's 2 obviously. There we go. Very cool. All right, just to move this along a little bit, I'm going to tell you what the numbers approach here. It's a very similar situation. If I was to graph this on the calculator and trace it out as x gets larger and larger and larger, I'm going to tell you that the y values get closer and closer to 4/3, as a matter of fact. And as a result, the horizontal asymptote is y equals 4/3. Pretty cool. All right, what would be your guess? Let's see if you could do this just guessing. Look at what it approached here. Look at the horizontal asymptote, and look at the function. Think about a 2/1 here. Here, I told you it goes to 4/3. Kind of look at that piece. Where am I getting that 4/3 from? And what would be your guess on this one? All right. Well, I'm going to give it to you, and then we'll do a quick look. In this case, the y values get closer and closer to 1/2. Do you see the 1/2? There it is. And so I have a horizontal asymptote, should be of 1/2. Look at the leading coefficients, guys. 2/1, 4/3, 1/2. Cool. Let's just check out that last one in a hurry here just to see. So I'm going to go back and clear that out. And what did I say? X squared plus the 2 divided by 2x squared minus x. And same deal, I'll just go right to the table. And do you see it? Again, we're in the 200s. And do you see the y values? Coming down slowly, getting closer and closer to 1/2. Pretty awesome, huh? All right. One more that I'll do, and then I'll kind of give you that piece, and let's get our conclusion in place. So I go here, and let's do the bottom row. Let's do function f. And I have x to the 3rd divided by x minus 1. I'm going to hit graph, and we get something like this, kind of intriguing looking graph. I have my vertical asymptote, of course, but here this is just shooting up as we go to the left. Hey, this is just shooting up as we go to the right. Does it look like it's approaching a particular number like all those other functions? No. And take a look here, guys. What's going on with those numbers? They just seem to be getting larger and larger and larger. Does it look like there's any end in sight? No. So is there kind of the same end behavior going on? No. And as a result, there's no horizontal asymptote. And I will tell you, there's no horizontal asymptote here, and there's no horizontal asymptote here. And before we end this lesson and do the last example down below there, you've got to come up with it. Why? Why did the functions in the top row have a horizontal asymptote of y equals 0? why did the functions in the middle row have a horizontal asymptote of y equals the ratio of those leading coefficients? Here's your 4/3 right here. And why did the bottom row not produce a horizontal asymptote? There are the three questions, guys. If we got those, again, within seconds, we could figure out a horizontal asymptote of any function pretty quickly. No graph, no table, unnecessary. All right. So think about it for a second. It'd be great for you to pause the video on this and really mull it over if you've got the patience and the inquisitive nature there. If not, I'll give you one hint, and then I'll give it to you. All right. Think exponents, guys. Think degree. Think degree on the numerator. Think degree on the denominator. Look at them all. Compare degrees. All right. And by the way, this would be like an x to the 0 here, and this would be like an x to the first, just FYI. And here it is. It's all just degrees of the numerator and denominator. If you notice the functions in the top row, the degree of the numerator, very simply, is less than the degree of the denominator. There we go. Perfect. Look at this, guys. X to the 0 on top, x to the first down below. X to the first on top, x to the 0 down below, x to the 0 on top, x to the second down below. Smaller on top and the bottom. When is there a horizontal asymptote equal to the ratio of the leading coefficients? Degrees are the same. So the degree of the numerator, and I'm running out of room here, but I'll see what I can do, degree of the denominator. So it's when they're equal. Excellent. Let's get it in. Does everyone see it? X to the first, x to the first. X to the first, x to the first. X squared, x squared. Degrees are the same. And last but not least, when is there no horizontal asymptote? Look at the degrees. Top bigger than bottom. So here we go. Degree of the numerator is greater than the degree of the denominator. All right. I think we've got it. Let's just take a minute or two and find the asymptotes here. 4 parts for 2 functions, everybody. When you get an opportunity, give me VA and HA for vertical and horizontal asymptotes. One more time right over here. I would love to pause on the video and make it happen. See if you could pull it off. See if you can go 4 for 4. Well, here's what I got. When I did vertical first, I looked to the denominator. What would make the denominator 0? 2. Also negative 2. So we should get 2 vertical boundaries at those 2 values right there. Horizontal, again, as quick as can be, guys. Just compare the degree of the numerator to the degree of the denominator. Smaller on top than on bottom, and so you know there's a horizontal asymptote. The end behavior, it's going to 0. All right, I moved over here, same deal. This I factored very quickly as x minus 7, x plus 3. Down on the denominator, and so as a result, 7 is excluded from the domain, get a vertical boundary. Negative 3 is excluded from the domain, and so we get a vertical asymptote right there. Horizontal, guys, look at this. It's quadratic on top. It's quadratic down on the bottom. So the degrees are the same, and so we go to the ratio of the leading coefficients, 2 on top, 1 on the bottom. In standard form, you just look out in front. And so as a result, y equals 2. All right, there you have it. Take a look at that if you get a chance. Some good foundational pieces with this rational function. And we'll go ahead and obviously clarify and do some more stuff on it on the next lesson. Thanks for listening to it, and let me know if you have some questions.